So I'll get right down to it. So I apologize I can't be there. I apologize I can't operate Zoom or PowerPoint sharing screens. So thank you, Aurora, for fixing that. So today the talk I'm going to give is really about the chemistry of liquid extractions, which we've already seen Aurora talk about, and Mark and others speak about in this method and symposia. So I'm going to motivate a little bit why you'd want to interfaces play in those. And then I want to then understand maybe some of the mechanisms that underlie chemical selectivity. So we'd like to understand some aspects of interfacial self-assembly. And to do this, we're going to use surface-specific spectroscopies that we use and develop in our laboratories. And we're also going to understand some aspects of how energy is transferred away from recognition complexes in these same molecules, but now that have been transported into the oil phase. To try to understand dynamics and how interfaces influence separations. So the person who did a lot of the work, and I should give credit to these people, Lou has done the spectroscopy. So I'm just here talking about it. He was a postdoc with me. He made a lot of these first measurements and spent a lot of time optimizing things. Faisal is a relatively new addition to the separations group. He's a synthetic chemist. He ran a lot of the separations that we're going to see, the wet chemistry, the synthesis. Nikki Thiel is someone that honestly came up with the idea to do this. So I'm talking about it, but if you think this is a great idea and want to give someone, credit for it, Nikki's the one that had the notion to do this. Slava's done some calculations for us in DFT to help us rationalize some of our results, and Uvi, Robert, and Yingzhang play a role in our group everywhere. They do lots of spectroscopic and characterization measurements. So these are the people that did the stuff. I'm just talking about it. So what is a chemical separation? Well, we're in the business of unmixing things. So the last week, we've seen people talk about the dynamics of mixing. We're in the business of undoing that. So sorry for the undo, but the reason we want to do this is a lot of things you want in a technological sense. You want to have a pure material to make new materials out of. You need a pure material to make a solar cell with. So you need to spend a lot of energy to separate ions, to separate species from really complex mixtures. So what we're after is a way to selectively pull out one or a few of those things from a very complicated, maybe it's an ore sample, maybe it's a mixture of nuclear waste, maybe it's a mixture of ions that are in solution that you dissolve. And certain things are more valuable than others, especially to the Department of Energy who funds me to do this. Certain things called critical materials or critical elements. These include the lanthanides that I will focus on today. Cobalt and lithium are also considered critical materials. That's because these are things that you'll find in your cellular telephone battery. And the problem with these elements is that they're everywhere, right? Lanthanides, rare earth elements are all over the place, but they're in such concentrations, they're such low concentrations that it's economically not feasible to collect them. So you end up getting most of your rare earth elements from one mine in China. Cobalt comes majority from the Congo. So there's lots of places where there's rich elements in certain places, but we'd like to have other ways to maybe recycle or acquire these things that don't require going through specific places. Another example of a separation that we're interested in is carbon dioxide from air. So carbon dioxide exists at really low concentrations. So it's a very hard separation, but at these levels, it's high enough that you have problems with global warming. So figuring out how to separate such a dilute mixture is a challenge. This also plays roles in hydrocarbons. And then people have seen probably in the news these so-called forever chemicals. These are fluorinated polymers that stick around forever. So how do you grab hold of these very hard to grab hold of things and isolate them? So what I'll focus on today is separating lanthanides. And one of the major ways that we go about doing this is using a technique called solvent extraction. And Mark already explained this very nicely in his talk. More or less what you do is you take a liquid phase, usually water, something with stuff in water, and you contact with an immiscible oil phase. And with the help of some ligands, these are molecules that adsorb at the surface, you can transport ions from one phase into another. So you can take your purple solution here, shake it up, and you can transport things that are, now you get this, reddish plus blue gives you the purple. You can separate these two different things based on, in this case, this is polarity. but you can design ligands that will separate and recognize ions and transport those across an interface. And that's what we want to do. And one thing we want to focus on here is lanthanide separations. And the problem with lanthanides is sort of summarized here in that this is a quote from Pimentel and Spratley, is that lanthanum, that's these groups of things down here, this row of elements, has only one important oxidation state in aqueous solution, the +3 state. With few exceptions, this tells the whole boring story of the other 14 elements, right? So chemically speaking, these molecules are very not interesting in aqueous phase, but application-wise, these things find themselves used all over the place. You have chemical processes that make use of these. You'll have catalytic converters used in fluid cracking, made out of cerium and lanthanum. You can use these materials in quantum technologies like atomic clocks and various qubits. These are used in optical and biological systems as tracer elements. You can make magnets out of neodymium and other sorts of rare earth elements. And they have an interesting mechanical properties that you might want to use. So while the chemistry of these elements is very similar, in the aqueous phase, that's what makes them challenging to separate, is they all kind of behave the same, but they all have different roles at the end of the day in various applications. So the problem that we run into is that the separations of these things are really energy intensive and generally non-specific in a way that limits their separation and their use. And my thought is that one of the things that underlies one of the problems is understanding the mechanisms of solvent extraction. So there's lots of different ingredients and lots of different processes that can take place during solvent extraction, and Aurora went over these very nicely, and Mark discussed a lot of them as well, is that for a separation to happen, you have to have ligands in an oil surface. They might self-assemble. There's lots of things that can happen at these liquid-liquid interfaces. You can have changing ion pairing interactions that then tune the interface in the solvation environment. And ultimately, what you're hoping for is for an ion to approach the surface, or maybe the ligand move into the aqueous phase, as Mark mentioned, form some sort of ion pair or assembly, and then transport back across the interface, right? All these things happen at the same time. This is not like a serial process. It's very complicated. This leads to a lot of complications in understanding the role of an interface and separations. So what we want to understand is get an idea of where selectivity comes from in solvent extraction. So there's a few different perspectives I'll show here. One of them is a thermodynamic view. So after you shake up this solution, at the end of the day, what wins out is the most stable complexes. Things with the largest negative delta G will end up going into the aqueous or the organic phase. So you can look at it from a thermodynamic picture where the interface doesn't matter at all, right? All that matters is how well you can bind things. And this results in something I refer to as a Hofmeister trend, where as you go from very small lanthanides to the larger one. So this is all good, right? We have a thermodynamic view, and you can define molecules now that facilitate pairing interactions by making molecules of functional groups interact with lanthanide ions in a specific way. So the traditional way to look at a separation is if you put functional groups in the right spot, they'll bind to the right things, and it's sort of like a Goldilocks situation. If you have everything arranged just right, attract certain ions over other ones. So you can make a separation based on maybe you pull out the light ones because you have the functional groups in the right spot, but then the heavy ones, since you don't have the functional groups in the right spots, you don't extract them. So there's a sort of tug of war you can have based on this size specific and these thermodynamic aspects. You can also look at something in a kinetic view, where you have maybe reaction rates are different, or as Mark mentioned the other day, you have some sort of competitive multipath reactions that you can leverage to map things in time. So what we want to try to do is, well, can we alter selectivity in chemistry using an interface? So instead of having just a thermodynamic view or just a kinetic view, can we somehow use an interface and these ion effects to design something at a surface that'll be selective to ions? So what we've done here, and this is work I won't talk about too much, is you can have different ions will interact differently at this interface. And this results in different structures that an amphiphile can take at a surface just based on these chemical interactions. So one of the hypotheses governing this work is that interfaces are templated by ionic interactions in unique ways, and this could provide a structural basis for selectivity in a kinetic sense. The other hypothesis we have is that rigidity, or the lack thereof rigidity, will allow you to interact where energy is funneled away from the recognition. So what we did is one way to provide reverse size selectivity, that is for the lighter lanthanides, is to use a molecule that has prescribed size and shape. This way the interactions are just right, they can hold on to ions in a perfect way. So you can do this with this molecule called macropod, where you'll have these lanthanides, they'll hold on because everything is just right. This fits the smaller lanthanides nicely. What we decided to do was let's take that molecule and we'll cut it. I'll slice it right here. And what you end up with is an open linear chain. And based on what people tend to think is...
We can't hear you.
Size selectivity. Okay, you can't hear me. As soon as you remove the size selectivity, you remove the ability to have a selective extraction. So when we make the experiment...
Can you make your voice? We can hear a little bit, but not well.
Size selectivity. So what we did is we did some DFT calculations, or Slava did, and he showed that these lighter lanthanides to the heavier ones, you get this assembly of this recognition head group where it coils around the lanthanide in a specific way. So as you go from the lanthanide to PCM, you get a difference in binding energy at 5 or 6 kcals per mole. And you can see there's different binding interactions that take place in there, but they all assemble into this sort of pseudocyclic structure that coils around the lanthanide. So this tells us there's a difference in the binding energies in a thermodynamic way, but it doesn't tell us anything about how they came to be or how they got into the oil phase. So what we want to understand here is how ions interact with these molecules at a surface. The problem with interfaces is that they're asymmetric. The stuff you have on one side is different than the other. And from a molecular perspective, this means you have incomplete solvation. You have surface charging that gives rise to electric double layers and molecular ordering that then screws up orientation and drives chemistry in unique ways. The other problem you run into is that they're really, really thin. So when I talk about an interface, I'm talking about a molecular monolayer, not something that's much thicker than that. And this is Aurora's work that she shows how water can be quite different when you move a monolayer away. And then they're dynamic. Like the chemistry you want to see happens away from equilibrium. If you sit around and wait till the end of the day, there's not going to be a very interesting interface that are left to study. So what we use is a technique called vibrational sum frequency generation that uses the symmetry breaking of the interface to report on the surface itself. And I won't go into the details of how all of this works. But what we can do is measure in infrared. It's essentially an infrared spectroscopy where you're measuring vibrations in the molecules themselves that are at the surface. And you can do this in different polarization combinations. So you put in different orientations of the laser light, and you can map out things like assignments and functional group tilt angles for the molecules selectively at that surface. So I won't go into all the details of what we can unpack from this, but know that in the case where you have non-specific extraction, this means you pull out across all of the lanthanides, right? That you pull them all across pretty much doesn't matter what it is you're putting in there. But if you want to get specific extraction, like what I showed before, you have to work at pH 4. And what ends up happening is you see there's these big differences in some of these spectral responses. Some of these peaks are, 1-to-1 ratio. Over here, they're quite different. And the point I want to make here is that there's a strong pH-dependent interfacial structure. And it looks like whatever this interfacial structure is here might be playing an important role in that they're prearranging to bind metal ions in some way. So if we take a closer look, this band here, we can assign to methylene groups that are on the tail and on the ring structure. And there's another group that shows up here that describes the coupling of these vibrational modes. And so this is all great, but what we find with this, the intensities of these bands don't really change depending on what lanthanide you put in. So that's a little bit disappointing. What we can draw is a structure, though, that looks something like this, where at the interface, you have the charged arms that grab onto the lanthanide are pointed into the aqueous phase. And this large increase in these CH2 groups is because all of those CH2 groups are pointed out of the interfacial plane. So it gives you bigger signals. The interaction of this lanthanide with these oxygens and nitrogen groups gives you this appearance of this Fermi resonance coupling peak. So this is great in that we can look, we have templating. The interface is templated, but it's templated by the pH, not so much the lanthanide. So if the interfaces are templated, but not by the specific interactions, what's giving selectivity? And what we think is happening here is that there's something about the stability of the complex and energy transfer around the interaction site. So there's two ways to describe selectivity on the femtosecond time scale. There's a biological perspective, where essentially you funnel energy away from the recognition site fast enough that thermal fluctuations don't let you throw away that molecule. They can't wiggle free. And there's the chemical perspective, where if you just bind tighter, it's just going to hold on tighter. You don't need to worry about that coupling. And proteins use this biological perspective to hold on to things until slow reactions. Chemistry, we don't tend to think of it this way. So our hypothesis here is that we can use 2D IR spectroscopy to measure the rate at which energy transfers away from the recognition site. So we do this by measuring something called a nodal line between an excitation pulse spectrum, and then we probe at a time delay later to look at, well, how did that spectrum change? It's a pump probe measurement. And depending on how that nodal line changes, as it becomes more and more vertical, we talk about something called the center line slope, you're going to end up getting this decay in the signal that tells you about how the initially prepared excited states changed in time. So the faster this takes place, faster this loses information, the quicker energy leaves that recognition site. So looking at the molecules that we're talking about, octadecylamine, if you take an infrared spectrum, we can see that the lutetium, gadolinium, and lanthanum have different spectral responses, that they shift, and that if you overlay these things on top of each other, that the heterogeneity that you'd expect is somewhat suppressed because these things are wrapped around the lanthanide. It doesn't tell you how many environments you have, and it doesn't tell you how energy is transferred away from the binding site. So when we take the 2D IR spectra, you can see how all those same sorts of shapes show up, but you can also see how the
Excuse me, so you have 5 minutes. Now we can hear you.
You have one molecular species predominantly in solution, but it also it tells you that the dynamics for lanthanum are quite different than what you see for lutetium. So if we plot those spectral diffusion rates, what we find is that lutetium has the fastest spectral diffusion and lanthanum has the slowest. So this is opposite what we thought would be happening for the biological processes. Or this is what you recommended to me at one point. This was your counterpoint, is wouldn't the tighter bonding thing just hold on tighter? And it does. You were right. So we see that this trend follows exactly what we see in separations. It seems like what ends up happening is that for the lanthanum complex, the energy flows out of that recognition site very slow. It's very rigid. Everything is held on very tightly. For lutetium, that energy transfers out very fast. And again, this is not what you'd expect from a biological perspective, but these molecules aren't as big as biological molecules. So to answer the question of what have we learned from this is there's two things. I'm not very good at making hypotheses because both my hypotheses were wrong. I'm able to identify those and then explain what's happening here is these assemblies form at the interface, but they form surprisingly rigid complexes that they're templated by the interface, but not by the ions. So the pH plays the dominant role here. All that the ions have to get to the interface and they can be extracted. And this is all driven by pH to form this pseudocyclic assembly. What this is also telling us is that the dynamics of these molecules, it doesn't really matter what ion, or it matters what, because it modulates how well that molecule can wrap around the lanthanide ion. And that seems to be the more important part. is that here we're still in this regime where chemistry wins. It's not so much about complex collective motions and coupled modes. We're still operating in a chemical sense. So the selectivity of this arises because it's a better fit. You're not relying on this Goldilocks situation where you have to wrap around just right. You're able to have molecules contort to give you a selective extraction in sort of a non-traditional way.
Okay,
so with that, I will end my talk. I apologize.
Yeah, thank you very much for that very interesting talk.
Problems.
Okay. Any questions or comments?
Thanks, Ben, for a valiant effort, and we did get something out of it.
Yeah, I hope.
So I was really interested in this last thing that you talked about, where the lutetium, we know it has, smaller, has a much stronger electric field, and presumably the atoms that are in direct contact with it are more rigid than for the lutetium. But somehow the overall structure of the rest of the molecule is providing this very different energy transfer. Is that the way you're thinking about it?
I've not thought of it like that way in terms of like the electric field and such. I mean, I look at it as just being, yeah, it's smaller. So this is going to have a harder time just looking at it more of a physical picture of you can't make these bonds happy at the same time you make those bonds happy.
I see. So you think there's some sort of rigidity in this molecule that even though this is smaller, it just can't wrap around it I'm thinking
a little bit that there's, yeah, it's not going to be able to fit this. So it's still, you have some of that size aspect that's here, that this lutetium is smaller, but this is able to move around a little bit more and is able to dissipate that energy a little bit more. So I don't think here the dynamics are telling you much about coupling the low frequency modes and stability as much as telling you that, yeah, you just don't have a very stable complex as compared to something like lanthanum. That make sense?
Yes. Any questions?
So Ben, you've got these really, really long alkyl groups on this ligand, and so is that really stabilizing your surface dynamics, the dynamics of the instantaneous surface a lot too? Is it pretty dampened? Do you know?
Yeah, so we put the really long tails on there specifically because we didn't want it to go anywhere.
Yeah.
We wanted it to sit there, and we wanted it to kind of sit around.
Yeah.
Take our time with the measurement. We started this before we saw some of Mark's work with the transport into the aqueous phase, and I'm kind of glad that we did because that adds a whole new level of complexity.
But do you think that it's possible for the dynamics of the instantaneous surface to be coupling, or if it wasn't so rigid and flat, like if the system was an extracting system, do you think it's possible for the dynamics of the instantaneous surface to couple to the dynamics of this arm wrapping process?
Well, I mean, this system does extract. So whether or not it's an extracting system on the timescales that we see, or if it's fluctuating enough, I don't know about that. Does that answer your question?
So it's a really slow extraction.
Yeah, it is a slow extraction, but it is a slow selective extraction.
Gotcha. Okay. So if you had, I guess I'm trying to understand this more generally, like what your ideas on this are, is if you had a more dynamic, more flexible surface, do you think you could have coupling of the mechanical motion of the surface with like the dynamics of these arms wrapping around?
I think the dynamics of the arms wrapping around motions are femtosecond, picosecond. So it depends on the time scales of these structural changes on the instantaneous water surface. So my feeling is that it's like some of your work where you have these like convex, concave environments. The different local chemical environment, I think, is going to drive what ends up pushing this thing across the oil phase. But I think that the time scales that these molecules, those motions.
Okay. Yeah. Thank you very much. Okay.